There are several chemicals that can be used to detect the presence of sugars, and in this video we're going to look at a few of the more common ones. These all use related chemistry, the ability or not of sugars to reduce copper-2 in solution. We'll start with failing solutions. This comes as two solutions, A and B, that are mixed shortly before use to produce the deep blue test solution. The sugars we're going to use are, from left to right, glucose, fructose, sucrose, maltose and lactose, and I'm including starch as well. We'll start by adding a few cubic centimetres of the sugar solutions to test tubes. Then we add a roughly equal amount of the pre-prepared failing solution. The reaction will in some cases happen at room temperature, but is extremely slow, so the normal method is to put the tubes into a hot water bath for a few minutes. As you can see, very soon some of the tubes start to show a characteristic red-brown colour. In very low concentrations the colour can be green due to a mixture of the reddish-orange and the blue colour of the copper-2 ions. And here we have the results. Starch, unsurprisingly, gives no result. The two monosaccharides on the left, glucose and fructose, produce a notable red-brown precipitate. The disaccharide sucrose does not, but interestingly the other disaccharides, maltose and lactose, do produce a colour change. In the reaction, copper-2 ions are reduced to copper-1 by the sugars in an alkaline solution. Copper-1 ions generally do not form stable soluble compounds, so the result is a precipitate of red-brown copper-1 oxide. You will probably be aware that if you add an alkaline solution to copper-2 ions, you will usually get a precipitate, a hydroxide or carbonate. In failings, the alkalinity is provided by sodium hydroxide, and to prevent this precipitation the copper ions are first complexed with tartrate ions. This prevents the precipitation. Monosaccharides have an aldehyde group, and this is what reacts with the copper. Ketose sugars can isomerise to produce an aldehyde group and thus react. In some disaccharides like maltose and lactose, the ring structures of one of the sugars can open up and release a free aldehyde group which, again, can react. In sucrose, however, the two sugars are bonded together in such a way as to prevent the rings opening, and thus there is no aldehyde group available to react. Another common test is Benedict's reagent. This is similar to failings, except that it comes as a single solution. The alkali is sodium carbonate rather than sodium hydroxide, and the complexing agent is citrate rather than tartrate. As before, we add it to each of the samples and incubate them for a few minutes in hot water. As you can see, the end results are broadly the same as for failings reagent, though some of the colours are slightly different. A less common variant is Sandell's reagent. This is similar again to failings, but is less alkaline, in that while still using sodium hydroxide, it is only 0.4 molar, and this time it uses EDTA as the complexing agent rather than citrate or tartrate. Once again though, the results are largely similar. There is also a variety of other reagents that can be used for similar tests. Barford's reagent, Selivenhoff's reagent, Bial's reagent, Molich's reagent, and many others, but these are the two, or possibly three, that are most likely to be commonly encountered in schools.